I'm sure many chemistry students have had a similar question that I had during the molecular geometry unit. Valence shell electron pair repulsion theory, or VSEPR theory, suggests that molecules are most stable when electrostatic repulsion is minimized. That is, when there is the greatest degree of separation between bonded atoms and/or lone pairs. Molecules like beryllium chloride with a steric number of 2 have bond angles of 180 degrees, an elegant angle that maximizes the separation of the two bonded atoms. Molecules like boron trifluoride with a steric number of 3 have bond angles of 120 degrees, also a nice whole number that evenly separates the 3 fluorides. But molecules like methane with a steric number of 4 have bond angles of 109.5 degrees, which feels very odd and awkward. So in this video, I will attempt to show why bond angles in a molecule such as methane with 4 identical groups bonded to a central atom is predicted by VSEPR theory as 109.5 degrees. Before we begin, let's define the mathematical notations and outline some simplifications and assumptions we'll be making. We will use a Cartesian coordinate system in 3-dimensional space, with the origin representing the central atom, and 4 vectors A, B, C, and D from the origin representing the positions of the 4 bonded groups. The vectors will be written in column vector form, with v sub x, v sub y, and v sub z being the x, y, and z components of vector v respectively. We also define the equation for the magnitude, or length, of a vector, the equation for the dot product of 2 vectors, and the equation that relates 2 vectors with angle theta between the 2 vectors. To simplify the math, the length of all bonds will be the same. In other words, the magnitude of all vectors will be 1. Secondly, we will be restricting the degree of freedom of 2 of the 4 vectors to make the math easier. The position of one bonded molecule will be 0, 0, 1, as denoted by vector A, and the position of a second bonded molecule, as denoted by vector B, will be restricted to the half yz plane where y is positive, so that the angle between vectors A and B remains unrestricted. In terms of assumptions, we would assume that a solution exists where all angles are equal for 4 bonded groups, and we would also assume that equal angles of separation is equivalent to the greatest separation between groups in accordance to VSEPR theory. So, let's get to the math. Since we have established that the magnitudes of all vectors are equal to 1, we can substitute the components of each of the vectors A, B, C, and D into the magnitude equation. The magnitude equation for vector A is trivial, but we do get some relationships set up for vectors B, C, and D. We can establish some more relationships between variables with the dot product equations. By taking the dot products between vector A and vectors B, C, and D, we deduce that the z components of B, C, and D are equivalent, since we assumed that theta is equivalent between all vectors. Taking the dot products between vectors B and C and vectors B and D show us that the y components of C and D are equivalent by inspection. Going back and rewriting the magnitude equations for vectors C and D gives us this equation, and since the y and z components of vector C are equal to the y and z components of vector D, the x component of C squared must equal the x component of D squared. Because C and D are distinct vectors, the x component of C must not equal to the x component of D, since all of the other components of the 2 vectors are equal. Therefore, the x component of C is the negative of the x component of D. Finally, we can write the dot product equation of vectors C and D and substitute some equivalent variables in them as well. Since we equated some variables and used some equations, let's rewrite our vectors and unique equations left. We have eliminated 4 variables from the vector components, namely the z component of C and all 3 components of D. We have 5 unique equations remaining, equations derived from the magnitude equation of B, the magnitude equation of C, the dot product equation between A and B, the dot product equation between B and C, and the dot product equation between C and D. With 5 remaining variables and 5 unique equations, let's solve for theta by substitution. B sub z is equal to cosine theta from the third equation, so we substitute in cosine theta for b sub z in equation 1 to determine that b sub y is equal to sine theta. In equation 4, substituting b sub y and b sub z gives us c sub y expressed in terms of theta. Substituting for c sub y and c sub x in equation 5 allows us to also express c sub x squared in terms of theta. And finally, in equation 2, we are able to substitute for all terms in terms of theta. After expanding and simplifying, we can calculate that the cosine of theta is equal to negative 1/3. That is, theta is roughly equal to 109.5 degrees. This was a very inelegant and limited derivation of the VSEPR predicted bond angle of a molecule like methane, with 4 atoms connected to the center. It's inelegant because of the restrictions put on the vector magnitudes and on the degrees of freedom on 2 of the 4 vectors, and it's limited because it cannot be used to determine the molecular geometry of molecules with steric numbers greater than 4, since the setup assumes that all vector pairs have the same angle of separation in a molecule with the greatest degree of separation between bonded groups, when this is not the case in molecules such as phosphorus pentachloride with a steric number of 5, or sulfur hexafluoride with a steric number of 6. Furthermore, the conclusion sort of rests upon the assumption that having the same bond angle between all vector pairs equals the greatest separation between groups, which is not proven in the calculations in this video. So a better proof would show that the greatest degree of separation of groups for a molecule with a steric number of 4 occurs exactly when there is an equal angle of separation between all bonded pairs. And a better model would be able to predict bond angles for molecules with different bond lengths and different bonded groups. One thing I noticed is that there is a trend to the bond angles in molecules with increasing steric numbers. The 180 to 120 to 109.5 degree trend might seem random at first, but once we realize that they can be rewritten as arc cosine of -1, arc cosine of -1/2 to arc cosine of -1/3, there seems to be a pattern. And from here on out, it is pure speculation. The 180 degree bond angle occurs when 2 groups are bonded to one central atom in one-dimensional space. The 120 degree bond angle occurs when 3 groups are bonded to one central atom in 2-dimensional space. And the 109.5 degree bond angle occurs when 4 groups are bonded to one central atom in 3-dimensional space. So perhaps the same relationship holds in higher dimensions where the bond angles can be equivalent in n-dimensional space, with the bond angle being arc cosine -1/n for n+1 groups bonded to the central atom, although this is probably not useful in everyday chemistry. Anyways, thanks for watching this video, and if you know any better proofs or models, which I'm sure there's plenty, or if you have some comments related to my speculation, please leave a comment so that all of us can learn more.